Hey kids, back to expected value, which we did in the last video, but we are going to add variance, something called variance, um, to our objectives. So you are going to be expected to calculate and interpret. Expected value, well, you already know how to do that, right? That's old. But now variance, you are going to be expected to do small data sets by hand. So I'm going to go through that. And by hand, it doesn't necessarily mean that you don't have your calculator by hand. When it says do it by hand, you still may be doing it with, how do I write this? With the calculator ability to just do basic math, where you add, multiply. You're going to have to add and multiply, square, things like that. But it is how you manipulate lists. So it was all that stuff that you did in AAF with manipulating those lists when you did like the Barbie project and the Cheerios project. That stuff is going to come in handy. And yes, I know you can do it in Excel and with a calculator, but when you're taking an IB assessment, it's the calculator that's going to be in your hand. You're not going to be able to do Desmos or Excel or any of those things. But then also with the GDC. Now, I hardly ever say GDC. This is graphing display calculator. This is IB how IB refers to a graphing calculator, a GDC. But what we mean by that is with its programmed stat features. No standardized test wants to waste time with you repeatedly adding or repeatedly multiplying lists of numbers. So when we say by hand, it just means that they're not going to want you to access, they're going to want you to set up and show the setup as to how the calculator has been programmed to get some statistics features. And hopefully that will, that'll become clear as I go through this video, but please do have your graphing calculator with you as you go through this video and as we are in our live session. So we did this probability mass function in the last video, where I first explained the notation with the discrete random variable x. The list of those discrete variables is finite. It's not infinite. It's just 1, 2, 3, 4, and 5. We made a little table like this, and I just kind of did it off into the side to show that it was a probability mass function. It was a probability distribution because all of the probabilities were between 0 and 1, and because the sum was equal to 1, right? So if you could fill in, now you're going to want to make a column like this. This is what I mean by hand. This is going to be an example of the objectives by hand. So make this column, have this column, and then leave space for some more stuff over here. Okay, because we're going to be adding, we're going to be building our columns. So here, what this is multiplying these two columns. And for future purposes, I'm going to write this. L1, L2, and L3. And if we fill in our L3 values, I don't need a calculator to say that's 2 out of 62. And then again, just verifying again, the sum of the probabilities is 1. And the sum of each individual x times its individual probability, what did we call that? That's your expected value, right? Of these. Pretend these were AP tests are graded out of 5. So pretend 1, 2, 3, 4, and 5 represented AP scores, right? What's the chance of getting a 1 after going through our classes, right? Our AAF, IB Pre-Cal, HL, and BC. It's a probability you get a 1. 2 out of 62, pretending there were 62 students that took the test. What's the probability of getting a 2? A 3, remember for AP, 3 is considered passing. A 4 and a 5. And this does, while we have more than 62 kids, we get more 4s and 5s than anything else, right? It's because each class is very purposefully targeted to prepare you, right? It is planning, vertical planning, AAF, IB Pre-Cal, HL to BC Calculus. You're going to do well, I promise. Or at least by taking our assessment, you're going to know where you fall on this. Anyway, that's a side note. So when I add up all of this, I'm getting the expected value. I got 258 out of 62, which is approximately 4.68. I'm sorry, 4.16. Again, exactly, I got 258 out of 62. But what does that say? Again, suppose these are AP scores. Given that you went through our 3 classes, right? The expected value is a 4, right? That's pretty good. And this is generally what our weighted average is. That's what we're doing, a weighted average. Our weighted average is above a 4. Sometimes we get like 4.5, sometimes 4.1, but we are always, at our school, at RM, our expected value is a 4. Pretty good. Right? It's a type of mean, a weighted mean. Okay, so hopefully from and somewhere in middle school, and then if you've taken AP Stat, right, a mean is just one type of average. There are other kinds of averages, right? There's the median, there's the mode. They're called central tendencies. So it kind of describes the middle of the data. Where can you expect the middle to be? And in this case, our weighted average, the middle is a little bit above a 4, right? Central tendency. A measure of central tendency. How does the data tend to look in the middle? Central tendency. That's what I wrote there. I forgot. Sometimes I forget what I type in. The expected value is a measure of central tendency. We got a little bit more than 4. But I want you to think this is a random scatter plot here, dot plot, if you will. The variance, and again, if you've taken AP Stat, you've heard about this, but the variance is not a measure of central tendency. It's a measure of spread. And it's usually spread from the center. That's what variance describes. So for instance, let's say that, I don't know, let's say that I have one of you that had a test score, you got 100% on a test, one test, and then you got an 80 on the other. What is your average? Right? That's your average, X bar, average, 90. But you scored 100%, you knocked out one test, and you did okay on the next one, but your average is a 90. That student is a different student, and I look at their performance differently from another student who scored an 89 on the first unit test and then a 91 on the second unit test. Their average, their central tendency looks the same, but those are two different students for me, right? Especially when you add more unit tests. So what's different? From the mean, right? 90, 100 is 10 units above 90, and 80 is 10 units below. 89 is only 1 unit away from 90, and 91 is only 1. This is a cluster. This student is clustered around the mean. This student is spread out from the mean. Even though the measure of the central tendency is the same, their dispersion is different. I want a way to describe the dispersion from the distance from the mean, right? So if you look at this data here, all of these people, pretty close to the mean, right? The mean's probably somewhere, right? If not that. These people, pretty close to the mean, but this one, they're farther from the mean. I would like a number to describe kind of the average distance from the mean. Spread. What's the spread like? Whoa, what the heck? What is this? All right, so take a moment, pause, calm, and let's decipher this. VAR is variance. This is our random discrete variable. The symbol is this lowercase sigma, right? Isn't that funny that capital sigma looks like this and lower sigma looks like this, right? It's like capital E looks like this and lowercase e looks like that. But notice that this lowercase sigma is squared. That's going to be important to you. Make sure you understand that. First, just a notation, then we'll talk about why. So again, let's talk about the fact that maybe this is the mean. So maybe this is 6.5. Let's pretend that's the mean. So I have 2 people that are, what, a half away from the mean. But so are 1, 2, 3 people are also a half. This is plus 0.5 distance from the mean. This is minus 0.5 distance from the mean, right? And I could do that for every single one of these dots. I could calculate how far are they from the mean, and then I could sum up how far they are from the mean. What's the problem with that? Could you add or sum all the distances from the mean? Each data point. You could, but what's going to happen? Right? For instance, these guys are going to cancel each other out. Most of them are going to come really close to cancel. As long as if you have the mean, by definition, means you have some data above and you have some data below. If you add their actual distances from the mean, you're distorting, you're artificially lowering the actual sum of the distances. So what can we do? What can we do? Well, you have a mathematical operation that takes every number, whether it's positive or negative, and makes it positive. Wouldn't you think absolute value? Doesn't absolute value take any number? So if you put the distance in here from the mean, if you take the distance from the mean and take the absolute value of it, then sum, wouldn't that be a decent thing to do? Seems pretty smart to me. What the heck? I get that there's a square. I get that squaring takes any number that is negative and makes it positive. But why squaring something makes it artificially large if you are over 1, artificially smaller if you are between 0 and 1. So when you sum all of those up, what the heck? Here's the reason that you're not going to understand until next year. Absolute value is not differentiable, and squaring is. And that's the reason you square instead of taking absolute value. It has to do with calculus. You will understand that next year. So that was a little deviation. You just have to know that the formula for the variance is the measure of dispersion from the mean, is a sum, capital sigma. It is a sum of each individual random variable and its distance from what? The expected value, which is the mean. Square that and multiply it times, oh, I meant to make that a capital P. Again, it doesn't really matter. Multiply times all the individual probabilities. Capital sigma, that's the expected value of every individual x minus the mean squared. I'm going to add all of those up. Right, this part is here. The standard deviation is not the variance. The standard deviation, though, is the square root of the variance, which takes that number that you've artificially dealt with by squaring and undoing it. So the square root of the variance gives you a better idea of the actual spread, and that's where standard deviation comes from. So we are going to add a column to this. And we're going to get our calculator out, and as I said before, we are going to get your calculator out and hit the stat button. And in stat, arrow over to edit. And in L1, put 1, 2, 3, 4, and 5. In L2, put 2, all these values, all the probabilities. And then over in L3, you're going to put all of these values, again, not hard to do. Okay. So you wrote these down already, but I want in your calculator to put this in L1, L2, and L3. And I'm going to show you how to use one variable stats on your calculator to get these numbers. But now to do this by hand, what you got was the expected value. We want to get the variance. So to get the variance, you need to take these values here in L4. So in L4, you need to multiply L3 and L2, right? So arrow up into L4, arrow up and make L4 dark. Right? So in other words, put your cursor on L4 and make it dark, and then type. Second 2 times second 3. enter. When you do that, your calculator will fill L4 with this product. Now what do we want to do? So you multiplied L3 times L2 or L2 times L3, it doesn't matter. Then what do we need to do? Sum L4. So second quit to your home screen and hit second list or second stat, sorry, which is list, which means you're going to operate on list. Second stat, arrow over to math, and choice 5 is the sum. Hit sum L4, which is second 4. And when you do that, right, you're going to get numbers in here. And then that sum is 1.167. Remember, the expected value was approximately 4.16. That's the middle. The average distance from the mean is a little bit more than 1, right? So the mean was about 4.16. Most people were in the 3, 4, 5 range, right? Pretty good, pretty cool. Now, that was a lot of and that's what I mean by hand. You just did this, you found by hand. Actually, remember, this is squared. So I shouldn't say the actual standard deviation, though, is the square root of the variance, which is the square root of that. So I shouldn't have said that first. .08 is the average distance. This is the average squared distance, right? Average distance, 1.08. Pretty cool. That's by hand. Even though you had the calculator, you do know how to manipulate your lists. When you do an internal assessment in math, this is the kind of thing that you want to have written down. You don't want to just say, I pushed one variable stats, but I am going to teach you how to do that. You ready? For one variable stats, which you can do on your homework, you do need to put in L1 and L2, but you don't need the rest. So you already have this in L1 and L2. Now hit stat, not second stat, stat, arrow over to calc. You want to do one variable statistics, but you don't want to do it on just L1. So you want to do one variable statistics, but you want to do one variable statistics where your list is L1, but your frequencies are in L2. And if you do that, where you put L1 for list, L2 for frequency, and then arrow down to calculate, oh my Lanta, look what it tells you. It calls the sum of what you had in L3 X bar. Oh, darn it, capital E's, which is your expected value. Do you see the 4.161290323 in there? And then look what else it gives you. It doesn't give you the sum of the variance column. It actually gives you the standard deviation. And it gives you the 1.08 number. Remember, you by hand got the variance. Take the square root of the variance and you get the standard deviation. Crazy. So that's what we mean by using the statistics capability of your calculator, where you're using one variable stats. Here you are still, when we did it by hand, we were still using the calculator, but we were actually stepping through every part of the formula. So here's some properties that you want to know. Properties of expected value and variance. So discrete random variable, and I have constants A and B. Look at what this statement says. The expected value of my random discrete variable multiplied by a number and then maybe added is just get the expected variable without multiplying and adding, and then go ahead and multiply your mean and add to your mean. Here's what that means. Here's our original data with our original probabilities. We got the expected value to be 4.16. But I was like, oh, oops, I have the same probabilities, but all my individual x's have been increased by 5. The new expected value is just 5 plus the old. I don't have to change my list and do it all again. So that's when B was 5. And A was 1. Right? I didn't multiply by anything. Look at this next table. This time B was 0. I didn't add anything, but my multiplier was 7, right? Every random discrete value was multiplied by 7, but I had the same originals and the same probability. So my new expected value was just 4.16 times 7. This was equal to 4.16 plus 5. There's a combo. Same original data, same probabilities. This time I did a combo where I both multiplied and added. Color those in the opposite way I said it. So that means my new expected value was 4.16 times 7 plus 5. IB loves these questions. And if you think about it, it should make sense, right? And I can actually calculate it as well, right? If you want to do it by hand. If you think about plotting this out, right, just on a number line, if you take every individual x and shift it up by 5, well, the mean is going to shift up by 5. Right? If you take every individual x and scale it by 7, the mean is going to get scaled by 7. And then this is just a combination of those two. But what about the variance? Variance is not as intuitive, I don't think. So if I have a variance, and remember we had what our variance was of this data. The variance was 1.167. Remember, the standard deviation was the square root of that. So what happens if I take each individual x and multiply it and or add something to it to change it? Let's think about this first. Let's think about this situation where a is 1, so I don't multiply anything, but I add 5. What's that going to do to the sum of the distances from the mean? Sum of the square distances from the mean. What's that going to do? This is the same, right? Right? It doesn't matter. If you do a shift to the spread, the sum of the spreads, the squared sum of the spreads are, sum of the squared spreads from distance from the mean, that's not going to change, right? Because she's taking the whole thing and shifting it up. So it doesn't matter whether you add 15, whether you add -2, whether you add whatever you add, the variance and therefore the standard deviation is not going to change. But look at this. Right? Again, this factor doesn't matter. Add whatever you want. Is not going to change the variable of the variance of the original. But what I should say. But here, I guess I could have kept that A. If you multiply every individual by x, the variance, take the original variance, don't multiply it by a, multiply it by a squared. Whoa. So in other words, here for this one, right, the variance doesn't change because I didn't do anything, right? This is just plus nothing. Variance doesn't change. Here, though, what happens? It's going to be my old variance times not 7, but times 49. And then this would be the same, right? Because this plus 5 wouldn't matter, not to the variance. All right, pretty cool. So we will do some more practice with this stuff in our next live session. I will see you then. No, I won't. I have another one. Forgot. I wanted to do this with you because I wanted you to watch out. So given a lottery, here's your outcomes. $5 for the ticket, and you lose. You lose that $5. You win $5, you win $20, you win $45. Those are your possible outcomes. You have an 80% chance of losing your original $5. 10%, 0.9, 0.1. Compute mu, which is the expected value, and R, or lowercase sigma. I know it looks like an R. Watch out. Is that the variance? No. That is the standard deviation. Watch out. Now, you're allowed to do this on your calculator. No one said not to. I have a calculator here. So if I want you to do this by hand, by making me a chart or whatever, I'll actually, and how IB would do this, would give you a chart and they would actually fill in some things and leave some blank and ask you to fill in the rest, right? That's what they would do. They're not asking that. They just said compute the expected value and the standard deviation. So you're allowed to pull out this calculator, put your outcomes in L1, put your probabilities in L2, run your one variable stat on your list L1 with your frequency L2, and get these values. Now be careful. If they asked you for the variance, what if they asked you? So this is right on my screen, 8.79, right? The lowercase sigma is right there. But what if they asked me for the variance? I could do two, right? I could just square this, but this is a rounded number, right? So what if they asked you for the variance? You could copy all those digits down, or you can do this, a nice little feature of your calculator that you're used to, just not in this context. If you hit vars, we usually hit vars for variables, not for variance, and arrow over to y vars. Don't arrow over. Just hit vars and look at choice 5. Statistics, hit that. Look at 4. Hit 4, and then on your and then you pop back to your home screen and hit squared. There's your variance. Kind of cool, right? But this problem did not ask me for variance. They did just ask me for the standard deviation. If $2 is subtracted from the outcomes, do you have to run a whole new one variable statistics thing and change all of your list one? You do not. You just have to take mu, your expected value, take the old one, and subtract 2 from it. So we had negative 1.25 minus 2. Now remember, this is money. So my expected, if I do this multiple times, I'm expecting that overall I'm going to lose money, right? That's the interpretation of this. How about your new standard deviation? What happens to your standard deviation? It's the same, right? And my variance, same, because I simply shifted everybody up. But if you dilate the outcomes, if you multiply by 2, what happens? Multiply but what do you do to the old variance, the old standard deviation? It's not 2 times what I had. It's what I had times 2 squared. What did I get out of that? Oh, I didn't write that one down. 4 times 8.79-ish. Okay. Not bad. Last thing. This really is the last one. How much would you have to add to these outcomes of your possible outcomes to make this lottery fair? What do you think fair means? Well, think about what our original expected value was. If we do this over and over and over again, expected value is a loss, right? It's a negative. Well, that's not fair. What's fair? If you go losing sometimes, but you should also win sometimes. So in order to be fair, what should your expected value be over many, many trials? 0, right? So if your expected value you want to be 0, but what is your expected value? I want to shift it. I want to shift this expected value to be 0. So what do you have to do? I want expected value. I mean, I think you can see here what it would be, but just to do it symbolically, I want the expected value plus my x's to be 0. So negative 125, plus this is my individual x, right? Plus all the sum of individual x's to be 0. So negative 1.25 plus those x's equal to 0. You need to take every individual x and add $1.25 to it. And then your expected value would be 0. Right? Pretty good. All right, now I'm really done. Now I can say we'll do some more examples in our next live session.